All right, everyone. So we are at week 13, and we are wrapping up simple harmonic motion. So we're going to go over position as a function of time with a mass spring oscillator first. Then we're going to get into how a pendulum works and the ideas going associated with that. And then we're going to review for the rotation and simple harmonic motion tests. So this problem we got in class, and it reads that a 2.14 kilogram cart is attached to a spring and it's stretched to the right, displacing it from its equilibrium to the positive amplitude. The system has a total initial energy of 11.23 joules. That was a typo on your sheet, so I think I corrected it. But hopefully, if you didn't see it corrected, you could fix it now. The equation displaying the function or position as a function of time is here. So this is our xt equals a cosine 2 pi f equation. So 2 pi f is equal to 4.189, and then the amplitude a is that 0.8 meters. The first thing we're trying to calculate is the spring constant. So because we know the energy, the spring constant, and we know the amplitude or the maximum distance stretched, so we can use the spring potential energy equation. So the maximum spring potential energy occurs when we're at your amplitude, so 1/2 k x squared, and x is equal to a at this one. And we're going to look for k. So we know, we know the amount of energy, 1/2 k, and then 0.8 squared. We're going to solve and do the math, and you should get something like 35.09 newtons per meter. That's slightly rounded, but that's the right concept. Okay, so then we are going to solve for what's the period of oscillation. The period of oscillation for a mass spring is just 2 pi square root of m over k. So m is 2.14, k is that value we just got. When you do that, you get 1.55 seconds. Then it asks you to graph the oscillation. So again, we're starting at the positive amplitude, and then we're oscillating all the way across to the negative amplitude and back. I did it 3 times because it fits on the graph 3 times. If you only did it 2, that's what it asked you to do. So this is what it should look like. So we're starting at the positive amplitude. The entire period, which I made 4 bars across, will get us back to that same positive amplitude of 0.8. So every 4 bars going across, 1, 2, 3, 4, that gets me back to 0.8, and then finally this is the end of the third one. When we're halfway through the oscillation, we're at negative 0.8, and then we keep adding the 4 bars to get to that. So this is what that oscillation looks like. Then it asks us to calculate a couple different things, calculate the magnitude of the velocity of the cart. So the magnitude of velocity, to get that, you're going to have to actually know the position, because the total energy, 3.5 seconds, if you look back at your graph, 3.5 seconds is not one of these like extreme points, so it's not all potential, it's not all kinetic, it's not at this either. So you're going to have to know both of those features. So I plugged into the equation at 3.5 and got a value of negative 0.4. Make sure you do radian mode here again, because if you're in degree mode, it's not going to give you negative 0.4. So then I solved for the potential energy when it's at time of 3.5 seconds, where it's at a position of negative 0.4, and I got 2.807. So that's how much potential energy it is. The total amount of energy is still the 11.23. So then after we have that, we can solve for the kinetic energy. So the difference between the total and the potential is what the kinetic is. And then I solve for the kinetic energy with 1/2 mv squared and solve for v, and got 2.8057 meters per second. So that's how fast it's moving at that point. Then it asks some questions about kind of just what's happening. So I looked at the graph. So I just took a picture of the graph from the time period that we want, which is 3.5 seconds. So if you're counting, again, we said the period of oscillation was 1.55. If we divide that in 2, it's about 0.75. So to get from the halfway through the oscillation, this is like 2.85, and then half of that would get us to this line. 3.5 is slightly past this first line. So that's kind of where I put a asterisk there. So this blue point is kind of around 3.5 seconds. We also know that it should be about a negative 4. So that should be 2 lines down, because 4 lines down, or 1, 2, 3, 4, 5 lines down is 0.8. So it's going to be like halfway about there. So that's okay for that point too. So looking at this, if we look at this, if we think about what direction is it moving, it's going from here and it's going towards the negative. So in our oscillation, it starts, whoops, wrong way. it starts over here on the right and it's past the 0 and it's over here and it's moving towards that negative amplitude. So that's going to be moving left. So I had it moving left. You could also do the slope of the line on the position versus time graph. So if I do the slope at this point, we get a negative slope. So that means it has a negative velocity. So that works as well. So those ideas with slope still work for our concepts. Part 6 says, is the cart speeding up or slowing down? And again, you just have to think about, okay, it's moved past the equilibrium point, which is where it would be moving fastest, and it's going towards the maximum extreme compression. So it's going to be slowing down in that time period as it moves that way. So that's what I wrote here. So it's slowing down and it's moving to the left. So that's really just a review of that position as a function of time equation, which actually still works for the pendulum. It models the pendulum behavior, and I'll show you that in a second. So jumping into the pendulum, this is a GIF of like pendulum motion. A pendulum consists of a mass of M that is attached to a massless rod or string. We usually talk about strings. And there's no air resistance, no friction, no outside forces. And it oscillates about the vertical equilibrium position. So the vertical equilibrium position would just be when it was hanging straight down. And we could look at the restoring force. The restoring force isn't like the spring constant, but this is very similar in nature. So it behaves the same way that the spring constant does. So the forces acting on here, we have the force of gravity, which is constant, and then the tension force is the force that actually varies as time goes by. But gravity is always constant; it's going straight down, and the restoring force is based upon mg sine theta. So as it restores it, so like as it gets over to the left, the restoring force tries to pull it back to the right. Same thing over here. When it's on the right, it comes back to the left. When it's at 0, there is no restoring force. So again, that's very similar to what we were talking about in this scenario. So I drew some pictures here of I have the GIFs of the mass spring oscillator oscillating from positive A to negative A. I have the pendulum doing the same thing, and they behave almost identically. If we look at the energy, this is an important equation. This is like to figure out how high the pendulum, this is called a pendulum bob, the mass on the bottom of it. You always measure from the center to the point of rotation. So that is your length L, that length going from there to there. And the height is the difference between the bottom point and whatever angle you pull it up to. It's important that theta is going to be less than basically 20 degrees. If you go past 20 degrees from the vertical, it does not follow simple harmonic motion anymore. We try to keep it at like 15 or 10. So this angle here has to be like less than 20. So so to do that, to figure out this height, you're going to calculate the length of the string times 1 minus cosine theta. Just to show you that this is the length of the string, which is L, which is constant. This is still the length of the string L. The difference in this height, which they call H, this looks like a right triangle, right? So if this is my angle theta up here, this would be kind of a side, maybe I'll call that Y. So that side Y, which is the adjacent side, would be cosine of theta equals Y over L, right? So if I solve for Y would be equal to L cosine theta. Just going through the trig here to make sure it makes sense. And then you want to find H, which is kind of if straight down, if this whole distance is L, and we want to solve for H, we just take L and subtract off Y. So if we do L minus L cosine theta, that's the same as H is equal to L times the quantity of 1 minus cosine theta. So that's the trig identity. I asked you to do that a couple times in some upcoming problems. So if we take a look at this energy and think about the energy idea, instead of having spring potential energy, the pendulum has gravitational potential energy. So it swings down and it swings back from a higher position to a lower position. As you can see here, like it goes up and down, and you can see in this picture. So it's going from gravitational potential energy to kinetic energy back to gravitational potential energy. Just like in the mass spring system, it goes from elastic potential energy to kinetic back to elastic potential energy. So it really follows the same exact behavior. So this chart should make sense. So when X is at the they said A is the equilibrium position, that's all at 0 because there is no displacement there. B and C, those are the positive and negative maximums. Velocity, the maximum velocity occurs when it goes through that equilibrium position, and the velocity is 0 when it's at the extreme points of the pendulum. So it stops there and it stops over here on the left side. The force is based on the acceleration. So the force is biggest when it's trying to return it back to the original position, just like it is here when the spring is compressed or stretched the most. So when X is the biggest, so is F. The acceleration and the force go the same way. The restoring force is opposite to the direction of the displacement. We talked about all this before. And then we already just talked about potential and kinetic energy. And if you understand this setup of potential and kinetic energy, it's the same setup in the pendulum. All right. The formula for the period of a pendulum is 2 pi square root of L over G. L is the length of the pendulum, and G is the acceleration due to gravity wherever you're at. So on Earth, it would be 9.8. If you were on some different planet, it would be a different value. The period and the frequency are still inverses of one another, so you could flip over this equation and get the frequency, but usually I just use T equals 1 over F, so that works as well. So let's go ahead and try a problem. So it says a simple pendulum consists of a bob of mass 0.85 kilograms. It's attached to a string of length 1.5 meters, so that's L. The pendulum is raised to point Q, so point Q is over here. And it's 0.08 meters above the lowest position when it's not displaced any. And then it's released and oscillates with a small amplitude of theta between points P, which is over here, and point Q. So it oscillates back and forth, swings back and forth like you would imagine with that GIF. On the first diagram, we're going to draw a free body diagram. So at point P is here over on the left. So the tension is in the string. And that's going to go up and to the right, so I drew that in green. And then the weight, or the force of gravity acting on the object, is constant, and that's going straight down. At the lowest point, gravity is still acting straight down, but the tension is acting up. So that's the lowest point. It says determine the speed of the bob at the lowest point. So if you think about this as sort of like circular motion, it's part of a circle because it's like swinging back and forth. That's like along an arc. You can use centripetal forces here. You could also use energy, which is what I ended up doing. So you could figure out that force, or you could do it with energy. Energy is, I think, easier, so sorry about that. So with energy, the gravitational potential energy when it's at a maximum should equal the kinetic energy at a maximum when it's at the equilibrium position. So those are equal, so the total energy stays the same. So mgh, that's when it's at the height at point P or Q. And then 1/2 mv squared, that's when it's in between, halfway in between those 2 points at the lowest position. So I plugged into that. I plugged in the mass, which is 0.085. I solved for V. I plugged in for m, g, and h. The m's actually drop out. But you can get the speed at the lowest position, which is actually its maximum speed, is 1.25 meters per second. The next two questions, it says at what positions will the tension be the greatest, and then identify one modification you can make to double the period of oscillation. So for the tension being greatest, this is where I got confused. You should talk about centripetal force here. So the centripetal force is equal to the forces acting along the thing, so like along the circle. So the biggest force occurs here. Oh, sorry. There we go. When you have the centripetal force, or the tension, going up, and the gravitational force going down. So at the bottom of the swing is where it's moving the fastest. That also makes sense because centripetal force is mv squared over r. R is the radius, so that's the length of the string, so that's not changing along the circular path. So it's all just at the bottom. Identify one modification you can make, so that's looking at the period equation. So the period equation is T equals 2 pi square root of L over G. You really can't change G unless you go to a new place or a new planet. I calculated the period just to check it out, and it's 2.458 seconds for this initial setup with the information they gave you. In order to make the pendulum get bigger, which is what you want it to double, you have to increase the length. So again, L is, it's the square root of L is directly related to T. So if you want to double the outcome, you have to make L 4 times bigger. So if you doubled it, this period, it would become 2.916. The only factor you can change again that really makes sense is L. You could also decrease G, and that would work as well, but you can't really decrease the acceleration due to gravity. So you got to put a 4 inside the radical to get a square root of 2, or when you take a square root of 4, you'll get 2 times bigger. So 4 times 1.5 gets you 6. So if you made the length 6, you would get a period which is twice as big. Okay. So that's kind of it for simple harmonic motion with the motion of a mass spring oscillator and a pendulum. So let's go ahead and jump into this review. So on this review sheet, it's taking you through all the concepts with like rotational kinematics, torque, the ideas with moment of inertia, rotational inertia, that concept of where the mass is located in distribution to R to establish how hard it is to rotate. It also deals with the concepts of like rotational equilibrium, so things balancing, and then it gets into the simple harmonic motion stuff with all the different ideas that go along with it. So in this first one, I already have stuff worked out, so I'm just going to talk through it. Otherwise, the video would be super long. So a 22.5 kilogram child is sitting 1.2 meters from the center of a merry-go-round with a speed of 1.1 meters per second. We're supposed to calculate centripetal acceleration and the net horizontal force exerted on the child. So the 22.5 kilograms, that's the mass. The radius that the child is sitting away is 1.2, and the speed is 1.1 meters per second. So I solved for centripetal acceleration using the centripetal acceleration formula, which is v squared over r. So it'd be 1.1 squared divided by 1.2, and you get 1.0083 meters per second squared. So that is the centripetal acceleration. The horizontal force is the force that's keeping the child in place. That's like the force of friction or something. So Fc equals MAC. And that's going to be the mass times that acceleration. So you should get 22.4, and I left off the unit. That should be newtons because it's a force. So first one's pretty straightforward, just plug it in. The next one, same thing. The blades in a blender rotate at 6,500 RPMs, which is the initial speed. The motor's turned off and it slows down and eventually comes to rest and stops, so omega F is 0. And the time it takes for that to happen is 4 seconds. We want to find the angular acceleration. We want to find how many revolutions it makes in that 4 seconds, and then how far does a point on the end of a blade travel linearly if the blade has a radius of 0.1 meters. So I just plugged into the kinematics table. So I had to do converting first, so I started here. So I had to convert 6,500 RPMs or revolutions per minute into radians per second, because that's what we were looking for. So you multiply by 2 pi and then divide by 60. You'll get 680.7 for the angular speed initially. Then you're using the angular speed equation omega F equals omega I plus alpha t. When you solve for alpha, you get negative 170.2 rads per second squared. And then for part B, you're going to plug in and solve for how far it goes around. So that's delta theta. So I used the one half quantity omega I plus omega F times t equation, plugging in, again, the variables that are up here. I got 1,361.4 radians, and then you got to convert it into revolutions. So I showed that work going this way. So you get 216.7 revolutions. For the last one, it says how far does a point on the end of the blade travel linearly if the blade has a radius of 0.1. So we're trying to figure out the linear, like how far it goes around in meters. So that's like the arc length. So that's S. R is the radius and theta is our angular. We don't want to use revolutions because that's not the right unit to get us to what we want. So you got to go back to the radians value, which is 1,361.4, and then you multiply that by 0.1. So you get 136.14 meters is how far it goes around. Then we're talking about the next question. So again, angular kinematics. This time it deals with torque. It says object, a merry-go-round, accelerates from rest to the speed in 34 seconds. Assume the merry-go-round is a uniform disk. That's the way you calculate the moment of inertia of disk. I will always give you the moment of inertia, rotational inertia calculation. So 7 is R and 31,000 kilograms is M. So you're going to plug in and get I. I did that first. So 1/2 31,000 times 7 squared. So you get that value. That's I in this equation. We're trying to get torque. So we're trying to get the torque. So torque is equal to I alpha. We don't have R or F or sine theta, so we're not going to use that equation. We're going to use this one. And then I used kinematics to get alpha. So again, just plugging in, very similar to what we did. You got 0.02 radians per second squared for alpha. So you multiply those in, you get 15,190 meter newtons for the net torque. Another one that's dealing with torque and angular stuff. So Potter's wheel is rotating at a constant speed of 18 rads per second. That's a positive 18. The friction force between her hands and the clay is 1.5 newtons. I made that negative because in order to slow down, it has to go the opposite way. So it's going to, if we had a positive force, then it would speed it up. It says how far or how large is the net torque on the wheel if the diameter of the bowl is 9 centimeters. So diameter is all the way across, so we need the radius. So 9 centimeters is 0.09 meters, and then you divide that by 2 over here, so you get 0.045 meters for R. So that's that value. F is the force that she's applying, which I said was negative 0.5. We're going to make the assumption she's applying a force exactly perpendicular to the motion, so like it's 90 degrees. So you get a net torque of negative 0.0675 meter newtons. You got to solve for alpha in the next part to get part B, which is how long would it take for the Potter wheel to stop. So I solved for alpha using torque divided by I. So I just took that value we just got and divided by 0.11, which is the I value. So you get the angular acceleration. Then again, you can plug back into your chart and solve for T. So the change in time over this is 29.3 seconds. Again, that's all there. You can pause the video and watch the work, like follow along with that. The next one's an interesting question. It's sort of a little bit more difficult than some of the rotational equilibrium stuff that we've done. So it says a 75 kilogram adult sits at one end of a 9 meter long board. His 25 kilogram child sits on the other end. Where should the pivot be placed so that the board is balanced, ignoring the board's mass? So the mass of the board is not important. So we're like trying to figure out where do I need to put the fulcrum in order for this to balance. So we sort of did this in the lab, if you came to the lab and did that. So we have 75 kilograms on one end, you have 25 on the other. And they should be balanced. The two torques should cancel out. If it's going to stay balanced, the rotational equilibrium is 0. So I just used RF sine theta for both of these. I'm going to make the assumption when it's balanced, it's horizontal compared to the force of gravity, which is down. So that's going to be 90 degrees. So that's just going to go to 1 again. So I have R F of 75 equals, and I called this distance from where the 75 kilogram mass is to where the pivot is, that's R. And then the difference between the rest of the stick is going to be 9 minus whatever that little piece is. So that's 9 minus R. And then that's the force of 25. The 75 and 25, that's mg, so this is the mass times the gravity for both of these. And then for the gravities, they can just drop out because it's the same value. I divided both sides by 25 just to make the math a little easier. So if you divide by 25 over here, you just get 9 minus R. If you do 75 divided by 25, you get 3R. It's because it's 3 times R. And then it's just solving in for R. So you take this R over, it becomes 4R, and you divide by 4, and you get R as 2.25 meters. So that distance here is 2.25 meters. The rest of the stick is 6.75 meters. And that makes sense because this mass is 3 times larger than this mass, so this mass has to be 3 times the distance away. So if you do 2.25 times 3, you get 6.75, which seems to check out. Okay. So those were the rotational kinematics and torque and rotational equilibrium problems with moment of inertia or other ideas. And now we're going to get into simple harmonic motion. So this one is the mass on the spring. So it says a mass of 0.74 kilograms oscillates on a horizontal frictionless surface at a frequency of 2.5 hertz with an amplitude of 4.5 centimeters. So lots of things told there, and I labeled it. I converted centimeters to meters, so 0.045 for that amplitude. It says, what is the effective spring constant, or what's K for this motion? And then how much energy is involved, and then what's the position of the mass at 1.35 seconds. So the first thing I did was I took the frequency and solved for period. So if period is 1 over frequency, it'd be 1 divided by 2.5. So 0.4 seconds is the period of oscillation. And then I used the period equation with that 0.4 to solve. So I solved for for K eventually. So it'd be T squared equals 2 pi, or I'm sorry, T squared equals 4 pi squared M over K, and then these two switch. So K is equal to 4 pi squared M divided by 2 squared, or T squared. And then you just plug in the values. So 4 pi squared, those are all numbers. M is the 0.24. T is this 0.4 squared. And then you get 59.2 Newton meters as the K value. Once you have that K value, you used it in part B to get the maximum energy. So the maximum energy would be where it's compressed or stretched, so at the amplitude. From the amplitude equation, you can figure out the amplitude as 0.045. So it'd be 1/2, 59.2, and 0.045. You're going to square the amplitude part, and you get 0.06 joules. So that was all it asked you to do for the energy. And then it wants to find the position of the mass at 1.35 seconds. So I used A cosine 2 pi ft, which is the position as a function of time for anything in simple harmonic motion. So A is 0.045, 2 pi is a constant, F is that 2.5, and then time is 1.35. So you just plug this in. Again, this has to be in radian mode. All right, so this equation is the only one that we deal with that has to be in radian mode. And when you do that, you should get negative 0.0318 meters. So that's the last one there for number 6. So moving on, another simple harmonic motion one, which is dealing with a pendulum. So we learned about the pendulum at the beginning of this video, so it's a good review. How long must the pendulum be if it wants to take 1 complete oscillation per second? So it's going over and back 1 oscillation per second, so the period's 1. The mass of the pendulum bob is 0.3. It's moving at 0.25 at the bottom of the swing, which is the maximum. And we want to know how far above the lowest point. So we're looking for like how high, what's H. And then we're going to solve for the degrees that you have to displace the pendulum to get theta. So T equals 2 pi squared of L over G. T is 1. Again, you're solving. This time we're solving for L. So you have 1 divided by 2 pi. We're going to square both sides. So it'll be 1 over 4 pi squared equals. That's just a number. I just didn't solve for it until the end. So L over 9.8. You take the 9.8 to the other side by multiplication, and you should get 0.248 meters for the length of that pendulum. So that's how long the pendulum needs to be. For the energy idea, the kinetic energy maximum when it's at the bottom of the swing is equal to the potential energy maximum that it starts at, whatever this maximum height is, which is what we're solving for. Again, you could use the mass that I gave you, or you could just be smart and say, oh, it just drops out anyway. So 1/2 v squared equals gh. We're solving for h, so I'm dividing through by g. So it's the velocity squared over 2g. So 0.25 squared over 2 times 9.8. You get 0.0032 meters, which is a reasonable amount. Again, we talked through this earlier in the video. So this height is equal to, I think I used y in the earlier, but the length of the pendulum minus a will give you what's the leftover part, which we call h. So I know this height from this answer. I know L from the length of the pendulum. So I can solve for a and get 0.2448. And then I just have to plug that in to the cosine function, because in this triangle, this side is 0.2448. And this is the whole length, so that was the 2.48, or 0.248, excuse me. And we're looking for theta. So this would be the opposite side. That's my hypotenuse. This is my adjacent side. So I want A and H, which is cosine ka. So from SOHCAHTOA, it's ka. And then you're going to solve for theta. And when you eventually do that, you get 9.2 degrees. So again, small angle approximation works for this problem. Last one deals with a satellite. So this is a FC centripetal force and FG, which we haven't talked about, but that was in our we hadn't talked about it up to this point in the review, but that is definitely part of your assessment, so we want to make sure you talk about it. So a satellite, which is 1,000 kilograms, so that's the mass of the satellite, M1, MS, whatever you want to call it, is moving at 8,000 meters per second. The satellite experiences a force of 9,500 newtons, which is FC or FG, same thing. We want to know the centripetal acceleration, so I just used the centripetal force equals mass times centripetal acceleration, so it's just 9,500 divided by 1,000. So you get 9.5 meters per second squared for the acceleration. B wants to know the distance between the center of the Earth and the satellite. That is easiest found by solving for R. in this centripetal acceleration equation. You can't use the gravity equation yet because you might not know the mass of the Earth. You could have looked it up and got the same thing, but it's okay. So I just used this one. So I rearranged this equation for R. So R equals V squared over AC. So it would be 8,000 squared divided by 9.5, and you get this large number here. That's slightly rounded. It's not exactly right. So if you went more digits, you'll get a bigger number, but that's okay. So it's a big distance, which is fine. For part C, it says we want to know if the same satellite was at the same distance from the center of distant planet with unknown mass. We want to solve for the mass of that planet, and it experienced a 15,000 Newton force. So when it was by the Earth, it experienced 9,500. Now it's bigger, so I would expect the mass of the planet to be bigger because it's at the same location, so it's at the same distance. The satellite hasn't changed, G hasn't changed, so this value for the mass of the Earth or the mass of the new planet has gotten bigger to increase that because of that direct relationship. So we basically just plug in all the numbers. So 15,000 is the force of gravity. We know 6.67 times 10 to the negative 11th, that's the gravitational constant, big G. Mass of the satellite's 1,000, and then the radius squared because the radius is the same radius as in part B. We're looking for MP, so again, you do all that work, and you get 1.021 times 10 to the 25th kilograms. That is larger than the actual mass of the Earth, which is only like 6.4 times 10 to the 24th kilograms. So that is the review. Again, if you can do those problems, I think you're in good shape, and you're prepared to do the test, both the take-home and the in-class one. So good luck. I will talk to you guys later.